You think about them, these huge machines, miles long sometimes, firing tiny, tiny particles near light speed and smashing them together. It just sounds, well, impossible.
It really does feel like something out of science fiction, doesn't it? But it's real, and the engineering behind it is just staggering. You've got this blend of precision physics, powerful electromagnetism, advanced material science.
It's the integration, I think, that's so impressive. Like you said, not just one complex thing, but loads of them all working together right at the edge of what's possible.
A real testament to what we can engineer, absolutely.
Exactly. And that's what we're diving into today, the engineering guts of particle accelerators. We've got some great source material that covers, the basics, but also gets into the really advanced stuff, even some theoretical ideas.
And this is for you, listening in, wanting to get a solid handle on these complex topics fast, have those aha moments without getting totally swamped in jargon. Think of this as maybe a shortcut to understanding this pretty complex field.
Yeah, a roadmap. We'll start with how they fundamentally work, look at the core engineering challenges, then move to the optimizations you see in big facilities like CERN or, say, proton therapy centers.
And then we'll peek into the future next-gen tech and even the really theoretical frontiers.
Sounds good. Ready to go deep.
Let's do it. So, at its heart, what does a particle accelerator do? It uses electromagnetic fields, really powerful ones.
Right. To push charged particles, could be electrons, protons, ions, that sort of thing?
Exactly. Push them to incredibly high speeds.
Okay.
And then, either you smash them together to see what happens, study fundamental physics,
or you aim them at a target for things like medical treatments, making specific kinds of radiation, or even producing new materials.
That practical side is really important. It's not just about fundamental science, though that's obviously a huge understanding. The universe's basic building blocks.
But yeah, cancer therapy, materials, the engineering has real-world spin-offs.
Definitely. So let's break down the main components. Where do we start? The particle source, right?
Makes sense. Where do you get the actual particles you're going to accelerate?
Well, if you need protons, often it starts with simple hydrogen gas. You just strip off the electron and there's your proton.
Okay. And for electrons?
You might use something called a thermionic source, basically heating a material until electrons boil off, or a photocathode, where light knocks electrons free. Think of it like the starting blocks for the race.
Got it. So you've got your particles. How do you get them moving, get them onto the main track? That's the injector system.
Precisely. The injector takes those initial particles, maybe ionizes them if needed, and then guides them into the main acceleration path, often using what are called RF cavities.
RF radio frequency.
Yeah. These cavities generate oscillating electric fields. Think of tiny timed pushes that start the particles accelerating down the line.
Okay, so initial nudges. But to get them near light speed, that needs a lot more power, right? More RF cavities.
That's right. The main acceleration path is lined with more, often very sophisticated, RF cavities. They act like precisely timed electrical pulses.
Timed how precisely?
We're talking gigahertz frequencies,
Yeah.
billions of cycles per second. As a particle bunch flies through a cavity at the exact right moment.
It gets another kick, another boost of energy.
Exactly. Like a surfer catching wave after wave, each one pushing them faster.
Billions of times a second. Okay. Now, that works for linear accelerators, going straight. But the big famous ones are often circular, aren't they? Like the LHC. How do you bend the beams? Magnets, I assume? Very strong ones?
Superconducting electromagnets, yes. Absolutely vital for circular machines like synchrotrons. They create these immense magnetic fields that force the charged particles to follow a curved path.
And the precision must be incredible.
Oh, absolutely. We use dipole magnets mainly for the bending itself. But then you also need quadrupole magnets.
Quadrupole? What do?
They act like lenses. They focus the particle beam, keeping it tightly packed and stopping it from spreading out as it races around the ring. Essential for stability.
Okay, so powerful magnets bending the beam, other magnets focusing it like a lens, all while these particles are going incredibly fast. Seems like hitting even a tiny stray molecule would be a problem.
A huge problem. That's why you need an extraordinary vacuum inside the beam pipe. We're talking ultra-high vacuum.
How high is ultra high?
Pressure's far, far lower than you find in outer space. Any residual gas molecules would cause the beam particles to scatter, lose energy, mess everything up.
Lower than outer space.
Wow.
So how do you achieve that?
It takes really robust pumping systems working constantly and very careful selection of materials for the vacuum chamber itself, stuff that doesn't outgas, release tiny amounts of trapped gas. Maintaining that purity over miles of beam pipe is a massive engineering challenge.
I'll bet. Okay, so Particles are sourced, injected, accelerated by RF cavities, steered and focused by magnets, all inside an insane vacuum. How do the engineers and physicists actually know what the beam is doing? You need sensors, right? The diagnostics.
You absolutely do. You can't control what you can't measure. Accelerators are packed with advanced sensors monitoring the beam's properties in real time.
Like its position, how many particles there are, its energy.
All of that, yes. Position, intensity, energy spread. And that data isn't just recorded, it feeds back into the control systems.
Ah, feedback loops.
Exactly. Sophisticated feedback loops allow for real-time corrections. If the beam drifts slightly, the system adjusts the magnets. If the energy fluctuates, it tweaks the RF cavities. It's like a constant high-speed self-correction process.
Keeping everything perfectly tuned on the fly. Okay, so the beam is racing around, high energy, perfectly controlled. What's the end game? What happens at the destination? Collision points, targets.
Depends on the machine's purpose. In high-energy physics colliders, like at CERN, you have beams colliding head-on at specific interaction points.
And huge detectors built around those points.
Massive detectors, yeah. They're designed to capture and analyze all the new particles that fly out from the collision, giving us clues about fundamental physics.
And for other applications, medical maybe?
And for medical uses, like proton therapy for cancer, the beam doesn't collide with another beam. It's directed very precisely at a target the tumor-delivering radiation dose. Or it might hit a target to produce specific isotopes or materials.
So either smash things together to see inside, or aim them carefully to create something specific.
Got it. This whole setup sounds incredibly power-hungry. And those superconducting magnets need to be cold, right?
Extremely power-hungry, yes. The RF systems, the magnets, the control systems, they consume enormous amounts of electricity. And you're right about the magnets. Superconductivity only works at incredibly low temperatures.
How low?
Near absolute zero. We're talking just a few degrees Kelvin. That requires massive, complex cryogenic cooling systems, usually using liquid helium. Keeping miles of magnets that cold is another huge engineering feat in itself.
Power and cooling.
Yeah.
Just massive infrastructure. It really is a monumental undertaking, putting all these pieces together. The scale, the precision, the power. It's almost hard to wrap your head around. It really is.
Yeah.
And we've really only just covered the fundamentals, ready to look at how engineers push these systems even further, optimizing for even more precision, stability, efficiency, like in the big modern facility.
Absolutely. The basics make sense, but how do they squeeze even more performance out? Let's get into the optimizations.
Okay, a really big one is improving those RF cavities. Modern accelerators increasingly rely on superconducting RF cavities. Remember niobium?
Ah, yeah, the material.
Exactly. These niobium cavities are cooled down even further than the we're talking below 2 Kelvin. Colder than the standard liquid helium temperatures used for magnets.
Even colder. Why?
At those temperatures, niobium becomes superconducting, meaning electrical resistance basically vanishes. Zero.
So no energy wasted as heat in the cavity walls.
Pretty much. It minimizes power loss dramatically. That means the energy from the RF source goes much more efficiently into accelerating the beam. It's a key reason modern accelerators can reach such high energies without needing, impossibly huge power supplies or being hundreds of miles long.
Makes sense. Less waste, more acceleration. You also mentioned higher gradient acceleration. What's the goal there?
That's about getting more kick per meter of accelerator, getting a higher energy gain over a shorter distance.
How do they do that?
By optimizing the cavity shape and, critically, suppressing something called field emission, basically. Stray electrons getting pulled from the cavity walls by the strong fields, which can cause problems. Yeah. By pushing these limits, engineers can achieve accelerating gradients over 50 megavolts per meter.
So particles gain energy faster, meaning you can build shorter, potentially less expensive accelerators for a given energy target.
That's the idea. A big win for efficiency and cost. Now let's talk beam stability again. Getting ultra-high precision.
Right, you mentioned feedback loops before. How advanced does that get?
Very advanced. You have to think of the beam not just as particles, but as these tightly packed wavefronts of charge. Keeping them stable requires incredibly fast, precise adjustments. We use active beam feedback systems.
What do they involve?
They use very fast-acting electromagnets that can make tiny corrections to the beam's position on timescales of nanoseconds. Billionths of a second.
Nanosecond corrections, wow. It's like digitally nudging the beam constantly.
Sort of, yeah, like a hyper-fast stabilization system. And then there's something even more exotic. Quantum beam cooling.
Quantum cooling. How does quantum mechanics cool a beam?
Techniques like stochastic cooling, which actually won a Nobel Prize, work by measuring deviations of particles from the ideal path or energy and then applying corrective kicks. It essentially reduces the random thermal-like motion within the particle bunch.
Making the particles fly in a more orderly, less spread out fashion.
Exactly. It reduces the beam's effective temperature, making it tighter, more focused. This is crucial for colliders because it increases luminosity.
Luminosity, that's basically the rate of collisions, right?
Precisely. A tighter, denser beam means particles are much more likely to collide when the beams cross. Higher luminosity means more data for the physicists. So cooling the beam means better science.
Got it. More collisions, more discoveries. What about the magnets? You mentioned quadrupoles for focusing. Any advanced tricks there? AI, maybe?
Definitely advancements in the magnets themselves, things like superconducting quadrupoles and even sextupoles for finer control over focusing and minimizing energy spread. But alignment is absolutely critical. Tiny misalignments can wreck the beam quality.
And that's where AI comes in.
Yes, it's starting to be used. AI models can be trained on vast amounts of beam diagnostic data to predict subtle drifts or misalignments in these focusing magnets before they become a major problem.
And even correct them automatically.
That's the goal. Predictive maintenance and autocorrection, leading to much more stable and reliable beam steering. It's like the accelerator learns to fine-tune itself.
Wild. Okay, and the vacuum. We talked about ultra-high vacuum. How do you push that even further?
It's a constant battle against stray molecules. Advanced techniques include cryogenic pumping, using surfaces cooled to extremely low temperatures, sometimes with superfluid helium, even colder than regular liquid helium, to literally freeze out any remaining gas molecules onto the cold surfaces.
Is trapping them with cold.
And material selection is paramount. Using specialized materials like titanium or ultra-high vacuum, UHV-grade stainless steel, that have incredibly low outgassing rates, they just don't release trapped gases easily.
And the pressure levels?
We're talking down to 10 to the minus 13 atmospheres, maybe even lower in some sections. That is significantly better vacuum than interstellar space. Maintaining that over kilometers is just an astonishing feat of material science and vacuum engineering.
Unbelievable purity. Okay, this is the cutting edge of current tech, but what about the future? You mentioned plasma wake field and laser-driven stuff, moving beyond RF.
Exactly. RF cavities are amazing, but they do have fundamental limits on the acceleration gradient, how much energy you can add per meter.
Yeah.
That's why researchers are intensely exploring these alternative methods.
So plasma wake field acceleration, how does that work out?
The idea is you fire a powerful laser pulse, or maybe even a dense particle, beam the driver into a plasma, which is basically a gas of charged particles.
Okay.
This driver creates a massive disturbance, like the wake behind a boat, but it's an electromagnetic wave in the plasma. This wake field has incredibly strong electric fields within it.
Stronger than in an RF cavity?
Potentially much stronger, up to 1,000 times stronger. A trailing bunch of particles, the witness's beam can then surf this plasma wave and get accelerated incredibly rapidly.
1,000 times the acceleration gradient. That could shrink accelerators massively.
That's the dream. Maybe tabletop accelerators achieving energies that currently need kilometer-long machines. The huge area of research. And related to lasers, you also have laser ionization sources.
For making the initial beam.
Yeah, instead of the traditional, sometimes bulky methods for creating ion beams, you can use ultra-short, intense laser pulses, femtosecond lasers, to precisely strip electrons off atoms. This can create very well-defined, highly focused ion beams, potentially leading to more compact and versatile accelerator systems.
Femtosecond. That's quadrillionths of a second pulses. Incredible precision. Seems like the field is really innovating, looking for fundamentally new approaches.
Absolutely. It's not just about bigger magnets or more RF power anymore. It's about entirely new physics principles for acceleration, pushing the boundaries constantly.
Okay, so if that's the near future, what about the really out there stuff? The next generation?
Right. Now we're getting into technologies designed to smash through the current energy frontiers, pushing towards, TeV scales and beyond, possibly with radically different approaches.
Let's hear it, straight out of the sci-fi proposals.
Well, building on plasma wake field, the concepts get scaled up. Imagine using a really intense driver beam, maybe from a conventional accelerator initially, or an incredibly powerful laser system to generate these plasma wakes over longer distances.
Still surfing the wave, but a much bigger wave.
Essentially, yes. The potential gradient is still that tantalizing 100 gigavolts per meter compared to maybe 50 megavolts per meter for conventional RF. The possibility of reaching much higher energies without needing tunnels stretching for tens or hundreds of miles is a huge motivator.
Tabletop TV accelerators. Still sounds amazing. What about even more miniaturization? Dielectric laser accelerators, DLAs.
Yeah, this is a fascinating one. Forget plasma. DLAs use tiny nanoscale structures, think intricate patterns etched onto a chip, made of dielectric materials like glass or silicon.
Nanostructures on a chip.
Exactly. You then shine carefully shaped ultrafast laser pulses onto these structures. The laser light interacts with the nanostructures to create tiny pockets of intense accelerating fields right within minuscule vacuum channels on the chip.
So you're accelerating electrons on a chip using lasers.
That's the concept.
Yeah.
It's still very much in the research and development phase, of course.
Yeah.
But the potential is there for extremely compact, possibly even disposable accelerators for specific applications, maybe portable medical imaging, industrial uses, tiny science experiments.
The complete paradigm shift in scale. Wow. Okay, what about this idea of magnet-free acceleration? How on earth do you steer a beam without magnets?
This delves into the complex world of collective effects within the beam itself. If you have a really intense beam, a very high current bunch of particles, its own electromagnetic field become incredibly strong.
The beam's own fields.
Yes. Under the right conditions, these self-fields can actually provide the focusing force needed to keep the beam contained. It's called self-focusing. By carefully shaping the beam pulse, you might be able to make it guide itself, reducing or even eliminating the need for external focusing magnets.
The beam becomes its own lens and guide rail. That could dramatically simplify things, cut costs.
Potentially, yes. It requires a deep understanding and control of how these dense bunches of charged particles behave collectively. It's a challenging but promising research direction. And finally, in this next-gen space, quantum-enhanced beam control.
Right, you mentioned AI before, but this sounds deeper. Quantum mechanics playing a role.
Two main ideas here, really. One is pushing AI, further developing AI-driven feedback systems that are almost autonomous, constantly learning and optimizing beam parameters based on subtle quantum-level fluctuations or correlations detected in the beam.
So AI managing quantum effects.
Maybe. The other idea is more profound, using quantum entanglement within the beam. If you could create and maintain entanglement between particles in different parts of the beam,
How would that help?
theoretically it could allow for unprecedented levels of synchronization and correlation. Imagine being able to ensure particles hitting a collision point arrive with their energies matched to an almost perfect quantum level. This could drastically improve collision efficiency, luminosity in future colliders.
Using spooky action at a distance to tune a particle beam. Okay, my mind is officially stretching now. Engineers are really thinking outside the standard toolkit here.
They have to. To push energy frontiers and make accelerators more accessible and efficient, you need these kinds of radical innovations, ready to go even further into the really speculative, bleeding-edge ideas where engineering meets quantum fields and exotic materials.
I think I need to recalibrate my definition of bleeding edge, but yes, take me to the deep end. Quantum fields, exotic materials. Let's cook in there.
Okay, buckle up. One concept is pushing beyond just quantum effects to actual quantum coherence. Think about using entangled particle pairs not just for feedback, but as fundamental components.
Entangled beams?
Potentially. Exploring whether pairs of entangled particles, perhaps generated together and sent along parallel paths or within the same beam, could be used to achieve sub-nanometer precision in timing and energy alignment at collision points.
How would you even control or measure that?
That's the massive challenge. It involves hypotheticals, like zero dispersion transport systems, where quantum entanglement correlations are actively used to counteract any tendency for the beam to spread out. Highly theoretical, naturally.
Sounds like it. What about these topological insulators you mentioned? How could a weird material help?
Right. Topological insulators are real materials, but with very strange properties. They insulate electricity in their bulk, but their surfaces are perfectly conducting.
Perfect conductors on the surface.
Essentially, yes, electrons can flow along the surface with virtually zero resistance. The speculative idea is, could you create beam pipes lined with such materials where the particle beam travels along this perfectly conducting surface?
Reducing resistance, maybe reducing beam spread.
That's the hope. Less interaction with the pipe walls, potentially much more efficient beam transport, especially for lower energy beams or perhaps in specific sections of an accelerator. And related to materials, there's the idea of metamaterials.
Materials engineered with unnatural properties.
Exactly. Could we design metamaterials that intrinsically guide particle beams? Structures that create tailored electromagnetic fields just by their shape and composition, forming self-sustaining waveguides without needing conventional magnets.
Guiding particles with the material structure itself? Wild. Now, even wilder. Quantum chromodynamics. using the strong nuclear force for acceleration.
Okay, this is really out there. Current accelerators use electromagnetism. QCD describes the strong force holding quarks and gluons together inside protons and neutrons. It's a much stronger force, governed by different rules, non-abelian gauge theory.
So could we manipulate that force?
Theoretically,
Maybe.
if we could somehow structure gluon fields, the carriers of the strong force, could we create acceleration gradients far beyond what electromagnetism allows? Some models even speculate about using quark-gluon plasma, that superhot soup of quarks and gluons, as a medium for transporting or even accelerating beams at incredible densities.
Harnessing the force that binds nuclei, the energy scales would be immense. Mind-boggling. What about different types of particles? Muons, neutrinos.
Good point. Most big accelerators use electrons or protons. But muons, heavier, unstable cousins of electrons, are very interesting.
Why muons?
Because they're heavier, they lose much less energy to synchrotron radiation when they're bent in a circle. Synchrotron radiation is a major energy loss mechanism, especially for light particles like electrons at high energies. So a muon collider could potentially reach much higher collision energies than an electron collider of the same size.
Less energy loss means higher potential energy. Makes sense. But they're unstable, right?
They decay quickly, yes.
Right.
That's a huge challenge, creating them, accelerating them, and colliding them all before they disappear. But active research is ongoing. And neutrinos, while they barely interact with anything, manipulating them is incredibly hard. But there are fringe ideas about using neutrino beams for communication, or maybe even energy transfer over vast distances. Very, very long-term thinking.
Muon colliders, neutrino beams. Fascinating possibilities. Okay, last one in the speculative zone. Structured light accelerators.
This builds on the laser ideas. But instead of plasma or simple dielectric structures, it involves using things like photonic crystals materials with periodic structures that manipulate light in complex ways to create precisely tailored electromagnetic waveguides.
Guiding the particles with light channeled through crystals.
Something like that. Or using sequences of precisely timed femtosecond laser pulses hitting the particles directly, providing tiny rapid kicks to boost their energy. Again, aiming for high gradients and precision, using light itself in very controlled ways.
It really feels like we're moving towards controlling matter at incredibly fine scales using light and exotic materials. This is far beyond just bigger magnets.
That's the frontier, pushing the fundamental understanding of physics and materials science to engineer new ways to accelerate particles.
Yeah.
And if you think that was far out, there's one more level, the absolute theoretical limits.
There's more. Okay, I thought QCD and entangled beams were the limit. What's beyond the bleeding edge?
Now we're venturing into territory where accelerator concepts meet truly exotic physics, even questioning fundamental principles like causality and dimensionality.
Okay, hit me with it. Causality conserving superluminal beam transport, faster than light beams.
Hold on, it's not quite warp drive. The idea isn't that the particles themselves consistently travel faster than light, which would violate causality as we know it. It's more subtle. Some quantum field theories allow for localized excitations or maybe specific modulations of the beam that could appear to propagate faster than light locally without allowing information to be sent FTL overall.
Like a wave pattern moving faster than the particles?
Perhaps something like that, or leveraging weird quantum vacuum effects. Of course, any such theoretical system would need built-in causality protection mechanisms, physics, ensuring no paradoxes arise. It's deeply theoretical, exploring the absolute limits of relativity and quantum mechanics in the context of beam dynamics.
Still, the concept alone is mind-bending. Okay, non-abelian gauge field accelerators. We touched on this with QCD, using the strong force.
Right, expanding on that. If we could truly engineer structured gluon fields or manipulate states like quark-gluon plasma in a controlled way, the acceleration potential could dwarf electromagnetic methods.
Yeah.
Imagine accelerator stages based not on radio waves, but on controlled interactions within the strong force itself.
Using the nucleus's binding energy to accelerate things. Astronomical potential.
Yeah.
Then extra dimensions. String theory in accelerators.
Yeah, this comes from theoretical physics frameworks like string theory, which propose more spatial dimensions than the three we experience. These extra dimensions are thought to be tiny, curled up, or compactified.
So how could they affect a particle beam?
The idea, purely hypothetical, is that at extremely high energies, particles might interact with these extra dimensions. Could we somehow use quantum fluctuations within these compactified dimensions, sometimes called Calabi-Yau spaces in string theory, to influence beam stability or steering, Or maybe even achieve acceleration through interactions with brain's higher dimensional objects postulated in these theories.
Okay, now we're really off the map. Steering beams by tickling extra dimensions.
It's about as speculative as it gets. It connects accelerator design to the deepest questions about the fundamental structure of reality. And finally, the ultimate energy challenge. Exotic matter interaction for vacuum energy harvesting.
Tapping into the energy of empty space, the zero-point energy.
That's the holy grail, perhaps. Accelerators consume vast power. What if you could extract energy from the quantum vacuum itself? Theoretical ideas involve trying to couple the accelerator fields to vacuum fluctuations, or maybe using exotic forms of matter or phenomena like the Casimir effect, where vacuum forces arise between closely spaced objects, to somehow amplify or sustain the beam's energy.
A self-powering accelerator drawing energy from nothing.
Or, more accurately, from the inherent energy of the quantum vacuum. It challenges our fundamental notions of energy conservation and thermodynamics. It's where engineering meets cosmology and quantum field theory at its most profound level.
Wow. Wow. From straightforward electromagnetic pushes to manipulating gluon fields and extra dimensions and vacuum energy, this has been an absolutely incredible tour through accelerator engineering.
It really highlights the sheer range of ingenuity involved, doesn't it?
Yeah.
From the very practical challenges of building stable magnets and powerful RF systems, all the way to these deep theoretical explorations. It spans so many fields of science and engineering.
Absolutely. And tracing that path from the core ideas we started with, using fields to push particles through all the clever optimizations, and then into these progressively more mind-bending future concepts. It's just amazing to see that relentless drive for more energy, more precision.
And constantly seeking a deeper understanding of how the universe works at its most fundamental level.
And for you listening, hopefully this deep dive is giving you a real sense of both the incredible engineering already achieved and the truly transformative potential still locked away in these future ideas. We're talking about technologies that could revolutionize everything from medicine to materials and fundamentally rewrite our physics textbooks.
It really does make you step back and think, doesn't it? Consider where pushing these boundaries might lead. If we could harness quantum coherence for beam control, or manipulate extra dimensions, or tap vacuum energy, how would that change not just accelerators, but our whole conception of reality?
Exactly. These aren't just engineering challenges anymore. They're probes into the very nature of existence. It's a profound thought.
And if any particular part of this journey sparked your interest, maybe it was the plasma wake fields, or the quantum cooling, or even the string theory stuff, definitely dive deeper. This field is moving so fast and there's so much more to explore. Your curiosity is what drives the next generation of discoveries.